The following webinar is presented by the E-Extension Farm Energy Community of Practice at extension.org and the University of Nebraska Lincoln Extension.
Hello, welcome everyone to May's edition of Bioenergy Friday web seminar. Our topic today is zero energy houses. We have with us Tim Hemsath, who's an architect here at the University of Nebraska and has some experience with these buildings and is going to give us kind of a primer on that and talk to us about this idea of zero net energy. And welcome, Tim. Thanks for joining us today.
Yeah, thank you, John, for having me. So I'll go ahead and get started and talk a little bit about my experience. Started back in 2006. The presentation, I'm just going to go through a little background first to start us off, and then I'll go into some detail of some homes that we've been involved with. I teach in the College of Architecture at the University of Nebraska Lincoln, as well as have a courtesy appointment in the College of Engineering in the Durham School of Architectural Engineering and Construction Management, because a lot of the projects that we've done have been highly collaborative, and trying to have a good team put together to pull everybody together has been an important part of our work. So the aspect of zero energy homes is essentially that the home itself, doesn't use any more energy than it needs, so becomes a closed system. When we started in 2006, the question was, can we do this? So there was a number of prototypes built nationally, just not in Nebraska, and the result is yes, we can do it. And now I think the question is, can we do it affordably? And so you see in the last year or two, Habitat for Humanity chapters in Minneapolis, in Iowa, both in Des Moines and Iowa City, in Wisconsin, and we're currently talking with the one in Omaha about, making zero net energy homes affordable, and that becomes the next challenge. And so I'm going to walk through some of our projects that have gone from this highly technological to very affordable zero net energy housing. And so what is zero, as John mentioned? And so the idea of zero or net zero means, there might be days where you're using more energy than you're generating, say with your photovoltaics. And so in that case, you're not zero. On, say, a day like today where it's going to get warmer, maybe it's cloudy or something, my air conditioner's on, I'm not generating very much power with the photovoltaics on my home, I'm not zero on today. But then tomorrow, maybe it's a little cooler, I don't run my air conditioner, and I'm generating more power from the photovoltaics on my home than I'm using. And so over the course of the year, then the goal is that you're net zero. And that goes the same with waste and water, that over the aggregate or the average over the course of a year gets to zero. And that works through net metering or monitors and being able to connect and pull power when you need it from the grid, and then return power when you're overproducing. So just an example of some of this. So the Living Building Challenge is another, the rating system for those who may know about LEED. It's kind of different in that there's different petals that they have that you can earn as part of it. And Zero Water's one. So this is the Omega Center. And so over the course of a year, annually, they use the same amount of water that they harvest on site. I kind of don't believe their statistics they give you on the website, because it's kind of ideal that their use is equal to what they harvest. And so then you can see for their energy use, they use, say, 37,190 kilowatt hours a year, and then they generate, close to 39,000 kilowatt hours a year. So they do that with photovoltaics on the roof or on site, and they can generate power. Or perhaps they have a wind turbine, smaller scale or something too. I just kind of wanted to show this example because of the statistics. And so this is the idea of net zero. Over the course of a year, you balance these things out. And so with waste, you would keep track of the amount of waste you generate in your facility, and try to, if you're doing other things with it than throwing it away. LEED has a criteria for construction waste recycled during the construction. And so that's another way to kind of measure some of these inputs and outputs of a building. And so zero energy, in the example of my talk, starts with the site, right? It's not just the building itself, but it's the landscape around. It deals a lot with the systems of the home, the mechanical, the heating and cooling, lighting systems. There's also aspects of materials to consider when you're thinking about zero energy, and aspects of design that I want to talk about today. And so primarily with systems, you're dealing with the overall building performance. When you're talking net zero, you're dealing with just the actual operational energy of that particular home, and that becomes net zero. And so it's about understanding the systems and when they need to be used and when they don't, in order to optimize your performance of the house. Net zero doesn't really take into consideration the amount of energy or inputs during construction. And so that's another term I'll throw out there called carbon neutral, which is taking into account all the inputs of energy of all the materials, the embodied energy that those materials have, that they embody because of the manufacturing and the energy and the fuel sources that went into the construction, the materials aspects. So net zero energy does not consider that. However, you can start to account for that, but it's not necessarily the framework that we've been focusing on. We've been doing the net zero approach, just looking at the annual and trying to balance that out over the course of a year. So from 2006 to 2010, there were a number of projects that we studied. So there were 5. 3 of them were built by faculty and students at the University of Nebraska, Lincoln. The other 2 by local builders. If I were to redo this today, it'd be quite different. There's actually home builders in Omaha build, one home builder in Omaha builds about 30 homes a year, and they're all net zero. Whereas in 2006, 2010, these were kind of just, one-off kind of little experiments. They weren't commonplace yet. And so I think that kind of shows the trend that's occurred over time, is that this has become commonplace in the market. And the question is then, how do we kind of further permeate that out? So I want to review these 5 projects just to give everybody an idea of the materials, the systems, some of the construction techniques that go into these homes. The importance, I think, is that energy efficiency in the home has benefits to communities in that saves utility dollars that we would normally pay for electricity, that can go back into the community. If the community overall can reduce their energy burden, that kind of embeds in a certain energy independence locally. And I think that has a large benefit to rural communities in Nebraska and Iowa and other states. We're talking with a number of communities in Nebraska about how to really ramp up energy efficient housing in the construction of new homes, and hopefully that leads to some more types of homes being built that are more energy efficient. So one of the first homes is called the Arc Space House, is built with a partner, NeighborWorks, which builds affordable housing across the country. Similar model to what Habitat for Humanity might do. This was a design build project by students at the University of Nebraska College of Architecture, and then sold by NeighborWorks to a family in Lincoln. And so some of the things that they did to kind of make this home more efficient was to implement a geothermal system, which for those who may be familiar with geothermal, instead of the air conditioner condenser outside of your house sitting there making loud noises, you get rid of that and you use the earth as your heat exchanger. And so instead you put wells outside that you bury the geothermal tubing in. The tubing then acts as the heat exchanger with the earth. So then you have a heat pump inside that moves the glycol solution around, and that's how you exchange your heating and cooling with the earth. It's far more efficient than a typical heat pump or other air-to-air exchanger. So all the homes, I think, that are zero energy capitalize on the geothermal because of the efficiency. While it might cost a lot more up front, the payback is very quick. Some of the other aspects of the home were just material choices and low VOC paints, as well as then flexibility within the layout of the plan, allowing modifications to be made with the loft space, so it could serve as unofficial kind of bedroom, but it allows kind of larger families to grow and expand, which then means you don't have to do as many modifications structurally to the home to accommodate different changes in use. So it is more sustainable long term. And it was ideally sited for southern orientation. So you can see on the left of the picture there some shades. Let me try this little pointer for you. So these little shading devices help to block the summer sun when you don't want it as much, but then lets the winter sun in for passive gains. So there was nothing to the south. There was just an alley, so it worked well. High efficiency doors and windows. The doors and windows are the weakest point in the home's envelope, and so investing in those really helps, along with just investing in a highly insulated envelope. The other thing to consider is the durability of the finishes you choose on a home. If you can, a lot of materials might not be as airtight or weather tight as others, and so you want to avoid moisture penetration into the envelope, keep it dry, which reduces the amount of chance of failure of the system. So durable materials, in this case like fiber cement, are potentially more airtight, more durable than other types of siding materials. Plus, they can be painted, whereas the maintenance-free vinyl siding that you see on a lot of developer homes, you can't paint that. You can, but it'll just come off. So the durability of that, and then just some site strategy with planning native materials and so forth. The next project, built in 2006 by Mike Rizak in Omaha, he actually lives there now and says he's pretty much living net zero over the course of a year. And so this project actually sits in whole development in Lincoln. It's a pond source geothermal system. So they submerge aluminum, like 3 foot by 6 foot aluminum plates in the ponds, and that acts as their exchange for the geothermal system. And the house also has a whole home control system, so it can monitor your electric use and generation. The home has 9 kilowatts of photovoltaics on the roof, and so With that and the net metering agreement with Black Hills Energy or the Nebraska Public Power District, they're able to exchange that. He's wired, or I shouldn't say wired. He's allowed for the expansion of the system by planning additional vertical chases through the attic to the roof. So if he were to ever want to expand, produce solar hot water, or to do other additional photovoltaics, he has the capacity to do that. So whereas the first home didn't have any photovoltaics, more of a case study in kind of the efficiency of a home. This one actually has the photovoltaics and actually produces energy and operates at zero net energy. The thing that this house has that was done really well is the framing. And so the attic and the walls are not, that crazy as far as thickness, but they're really well done, well constructed, highly airtight, and have art values of 23 to 27 for the walls, with art values of 50 to 60 for the roof. And so that's quite a bit more than you're required to, but that helps with the airtightness and the insulation of the envelope, which is one of the first things you want to do. You can also see in this home, use the pointer again, the architect, Michelle Penn, talked a lot about kind of maximizing the glazing on the south and then modeling out these overhangs to make sure that proper shading. There's not a lot of windows on any of the other facades, so most of the views and light is actually conveniently to the south, and so the windows are all there. There's just a few windows on the east, north, and west exposures, maximizing in the glazing that you're required to have on the south. So some smart design aspects incorporated there. The other thing Mike Rizak did was put in a air exchanger, so there's a constant volume of air being exchanged in the home. I think he said at the start they have about a third air change per hour. And so you're required to have a certain amount of air because of the tightness of the home. You need to have mechanical ventilation, and that comes through then the furnace, so it's filtered air. And so the actual air quality of mechanically ventilated homes is often better than those, not because it's bringing in that fresh air in that case, so that it removes then the allergens and other things that might lead to it. So the basement also then has a radiant floor system just on the basement slab, and that helps to kind of control heat during the winter. Summer makes it feel warmer, as well as then it has down insulation underneath. Insulation under the slab is not something that's required, but it's actually, with changing codes today, one of the more important things to do, and you would always do that if you did a radiant floor system in general. The next house was one that we started as a research house, so we've called that the Zero Net Energy Test House. So Zenith is the acronym. We imagine this one to be, zero net energy, primarily through the use of geothermal, the energy recovery ventilator, which I'll explain a little bit, some photovoltaics, and a really airtight envelope. Those were the kind of main strategies we employed. I like to call this one, let's try every technological gizmo we could at the time to see how it worked. Dr. Schwer at Peter Kiewit Institute kind of led the effort, and it seemed like every month he was going to put something else in it, which is great, because that's the idea of a test home. You don't quite know what's going to work, so let's try as much as possible to make it work. And as well as in an energy management system to kind of control some of those things. So the geothermal wells were put in. There's a number of different loops installed. They use primarily the vertical ones, but there are horizontals and others. The vertical ones are hooked up now. I'm not sure if Dr. Schwer plans to hook up the others or not. The energy recovery ventilator is becoming more and more popular because of the costs go down, but it's quite an expensive piece of equipment just to exchange your air in the home. But what it does is it takes most of the zero energy homes are tight, you need mechanical ventilation. When you bring in air from outside into the home on a cold day, that air can be very cold. And so your mechanical system then has to work harder to heat up that cold air to the temperature you need. Or on, say, a hot summer day, you have to dehumidify and cool that air down to a level that's at the comfort level of the home. So what an energy recovery ventilator does is it exchanges the outgoing air, so the air inside the home is exhausted at the same time the exterior air is being brought in, and uses that through a special filter to temper that air so the mechanical system doesn't have to operate as much. And so that's the concept of an ERV, as they're called, or an HRV. ERVs are much more popular and commonplace. There is 1 kilowatt photovoltaic laminate panels, so instead of the just the 4x8 panels that you see on the roof. There's also then the plan for a wind turbine to put in. We got a building permit to do this as an experiment, but Dr. Schwer just couldn't find residential turbines that actually deliver on what they promised yet, so he hasn't installed anything like that. This home has one of the highest HERS ratings at the time in the state, with a HERS of 38, I think that's next to my slide here. Yeah, so 38. So with the envelope, the windows, the mechanical systems, an energy rater, as they're called, comes to your home and does a blower door test, tests the infiltration, the air tightness, accounts for all the systems and the insulation and how you've designed the home, and gives you a score. A HERS index of 100 would be, the average home of this type. And then a HERS index of 0 would essentially be zero net energy. So this has a HERS index of 38, whereas the HERS index of the Madison home previously was 7. So this had a HERS of 7. And so, and I can't remember if that accounts for the photovoltaics or not. So you can see that the lower your score is, the better you're going to be towards it. And the goal of doing the HERS is it just certifies and verifies that you're meeting the performance requirements of Energy Star, and also that leads to being far more energy efficient. And it's a pretty well established certification system nationally that does this. The goal would be to do blower door tests and have your energy rater come out at multiple points throughout the construction, so you can test air tightness and address it before you get too far down the line. I could talk a little bit about that more on the last slide. This was an example we wanted to do because Hearthstone Homes in 2008 to 2010 was one of the fifth to seventh largest home builder in the country, working out of Omaha, and they were building all their homes in 2010 to the Energy Star certification, which is what the HERS rating will do. And their HERS scores were all in the low 50s, meaning they were all 50% more energy efficient than homes being built across the street by the other home builder. And so they really did this through a number of just low cost measures, and I'll go through a lot of those next, so I won't bore you with the flyer here that kind of goes through all these things. But I actually have more detailed examples later in the presentation. And so these best practices come now. So there were 20 best practices. This just explains the home mid-range cost. I think around 140 to 150 was the cost, about a 1,500 square foot home. We studied this and then we applied it in the construction of Zenith 2 because we wanted to move from, so Mike Rezak's home, the Madison, was $650,000. The Zenith was around $350,000. And so we wanted to get down to something more, less than $150,000 and still be zero net energy ready with the photovoltaics to reach that understanding. So some of the things that we did, right, is first air barriers. This is the envelope. This makes sure you have an airtight envelope, which is one of the first and most lowest cost things one can do in a home, is make sure it's airtight. And that deals with making sure if you have attic access, you're sealing that. Making sure your drywall and your ductwork are all sealed, and the top and bottom plates all have proper seals because those are the highest points of leakages. Any kind of drafts between the garage you want to seal, particularly if it's attached garage, make sure there's no air exchanges happening there. Garages aren't conditioned typically, so you don't want to be losing heat and cold through the wall between your home and the garage. Any rim joists around the perimeter, which is where your floor framing comes into the foundation, or your roof framing comes into the wall, make sure those are sealed. In this case, they sometimes have bedrooms above the garage, and so they want to make sure that they're sealing the ductwork and they're sealing that properly so that those bedrooms aren't cold above the garage. And then just sealing the wall framing. Insulation, they had a number of different ways, and the goal here with insulation is making sure it's continuous around the entire perimeter or envelope of the home, which is, when you start to really get into it, you can see it's quite complex. These are all the different things they had to do to make sure that that insulation was continuous. We lumped in, I think, in this energy efficient windows into it because it's part of the envelope rather than a standalone thing for our study. And then as far as systems go, we were just looking at the difference because they went to a 95% efficient furnace, which means they could remove some louvers and they could decrease the equipment and save some money overall. Kind of the lower efficiency furnaces needs an air louver to allow air movement into the home. Sorry if you can hear my phone buzzing. Silence that. So that was the system solution. We modeled all these out. They had a number of different home plans they delivered. We wanted to see how they stood against code with, I guess we call the current best practices. So if we look at the 2006 IECC, which at the time was the current code, and you can see the total kilowatt hours and mega BTUs compared to the codes in this table, and see how their best practices exceeds code in every case. And then we looked at the Building America benchmark, which is a house standard published by the Department of Energy, managed by the National Renewable Energy Laboratory. So they established this benchmark, which is a code compliant house, and gives you settings for R values for the envelope and U values for your fenestration of windows and so forth. So use that, and then we can then apply the best practices. So those packages I reviewed earlier relative to the air barriers, dealing with infiltration, the insulation, the windows, the attic, and the furnace, to see how we decrease off the benchmark. And so you can see overall, we do a pretty good job just with the best practices that were incorporated, which can be summarized here. And you can see that with each of these best practices, infiltration becomes the biggest point, with the insulation and the furnace kind of coming in next. So if you this helps to give you a priority here to understand. Well, I'm going to invest. Make sure I have an airtight home. Then I'm going to invest in my furnace. As you make it airtight, though, the one thing they do have is with the furnace, they do have a constant volume of fresh air coming in to their homes, which is just a cheap, $300 to $500 fan that you install that brings air into the ductwork, return ductwork, so that you have to bring in constant air. Hearthstone did that and actually found that pressurized the home slightly when exhaust fans weren't in, and that actually did quite a bit to reduce actually radon issues. They went from about a 20, I don't remember the number. It was something like 10% of their homes had to have radon mitigation. And then once they did these constant volume air intakes and mechanicals, they went down to like 1 or 2% of their homes had to have radon mitigated. The state actually came out and inspected because they thought they were lying on their reports, but they weren't. It was just a change in technology. So some of the framing techniques that Hearthstone used was they panelized the construction to come out to the site and be erected rather than framed on site. That allowed greater quality control with the connections. A lot of the panels and how they went approach were detailed so that it could be properly insulated across the envelope. So this is just an example of one of the panelized cavities. They have top plates so that the insulation at the top of the wall is enclosed. Enclosing insulation in all your wall cavities is important because if you have air exchange, it reduces the efficiency of the insulation. So they have these top plates to seal off all the walls and produce airtight cavities for the insulation to go. Then with you have a cathedral ceiling and then you have a lower ceiling, there's this wall between the uninsulated attic space and insulated or conditioned space. And so this area identified here allows them to insulate that wall at the same level as the exterior wall, reducing the heat exchange in between that wall. This is something that might get missed in other homes, where they might just kind of, throw some bats in there without putting this OSB back on, which allows them to put insulation in there and not have air going into that wall or the knee wall. The cantilevers, structural code requires some lateral bracing so you don't get torque or twisting within the cantilevers, and so that makes it very difficult to insulate the floors and the roofs of those cantilevers. And so they worked out this detail to allow you to blow in bad insulation underneath. The air barriers, the trick's the right type of sealant, making sure, again, it's visible to inspection and it's continuous across the envelope. So you can see, it's easy in their homes just to see that everything's sealed properly between the corners, the sill plates and between panels, as well as the top plates and rim joists. You can all very well see with the spray foam, they're able to see that it's done and that they're meeting the standard that they've set for their homes just with the visual inspection. Allows them to kind of do this. The attic access, so they had a ceiling access to get to the attic, so they devised this kind of system here to allow these OSB walls so that the attic insulation could have its depth. Often you'll lose depth at the attic access because it'll fall out, right? Once you open that attic access. The other thing is the attic access usually isn't insulated itself. You lift it out and you put it back in. Doesn't do any good. So they had this just unfaced cap that you could pull in the top and keep insulation in there throughout. So with the insulation, just continuous R value around the envelope and encapsulating it, which we talked about. So you can see they use spray foam and unfaced where the rim joists are, and then they have blown in bat within the cavities. And they went through a number of different ones and eventually found blow-in that doesn't settle, and keeps its performance over time pretty well. Just again, quality control, making sure that they install these sheets. They can just go in and see that this is what was installed and how it worked. Allows them to make sure everything's being done. Your attic, you can see, have 18 inches. 17 to 18 inches of insulation blown in. Even if they have a stair near the exterior wall to the foundation, it's kind of hard sometimes to get insulation in there, and so they use these foil-faced foam insulation. They lamented it's the most expensive insulation in the house, but it really does a great job to identify and keep that insulation continuous across the envelope. The ductwork, they have these return plenums, making sure that the drywall sealed so you're not getting leakages from other cavities and so forth in the home. And then again, all the ductwork was sealed. And so all this study kind of culminated in the Zenith 2 at Hummel Park, which we built for around $120,000. It's 1,000 square foot, 2-bedroom, 1-bath, just caretaker's residence for the park. Trying to build on these best practices and expand a little bit beyond what was done. You can see the final product here. Again, we used a fiber cement board. We kept all the penetrations out the rear so you don't see them, and then keeps them all in the wall rather than the roof, which is important. So the penetrations were here in the wall versus the roof. You can't see it in this picture, but the attic access is here via the outside. Really, there's no reason to get in your attic unless you want to store stuff, and you shouldn't really store stuff in your attic anyway. So we just put the attic access on the outside in this case. So that removed any and eliminated most of the penetrations through the attic, which has the most insulation in the envelope. So the idea being to reduce those penetrations means you have a more energy efficient envelope. You'll notice there are casements. Casements are more airtight than double hungs. So we used casements around the home. We have an energy monitoring system. You can see all those cords there that connect to the circuit breaker to collect data on energy use. We haven't downloaded it yet. We're going to do that this summer. Been 2 years, so we're going to collect that data and see how we're doing. We installed LED lights in the home, so all the lights were these expensive lights we bought. Actually, the light bulbs are more expensive than the light fixtures. At the time we did this. So a shot of the attic here. You can see at the wall, the top of the wall, all these holes have been sealed so that there's no air leakage in and out of the exterior wall, as well as then at the other perimeter, you can see the baffles that allow air ventilation to come from the eaves. This is all well insulated too around the perimeter, making it a very airtight envelope because you typically don't want air leakage through the walls and the ceiling into your attic. So that eliminates that. And then we did about 20 inches of insulation, which is about an R60 I think you get when you do that. And so just some of the modifications I reviewed is we had an exterior attic access, penetrations through the wall. We had an energy heel truss, so I can go back a couple of slides, you can see that. So at the perimeter here, there's this depth, and this allows the attic insulation to maintain its depth all across continuously throughout the attic space. And that's an add. In the typical truss, you wouldn't have this bump up here. This pink line would be down at the down here. So this is the added space you get in the attic with the energy heel, which allows that. So there's a question about, can you receive a copy of the PowerPoint? John Hay has this all recorded, so I would just reference the recording. So you can I could also send John a copy of these flyers, which can be downloaded on UNL's Digital Commons site. So this report's all available through that Digital Commons site. So this just summarizes Zenith 2 again, our attic, our energy heel. We used a double stud exterior wall around the perimeter. So we could increase the wall value, the R value in the walls to R30. We used a geothermal heat pump. We had not originally planned to do that. We planned to do the 95% efficiency furnace, but the city wanted a heat pump so they didn't have to worry about somebody stealing the copper out of their conditioner outside. So we did install window shutters. We were planning to make them operable so you could shut them, but you cannot imagine how expensive operable window shutter hardware is. So we ended up not making them operable, which is unfortunate. I really wanted to. Again, we used cement fiber insulation or exterior siding, fiber cement boards, and then we used highly efficient windows and doors. We had probably some of the most efficient windows at the time put in. We had a really great deal. The U value of 0.16. The typical U value of a window is 0.3, and so we got quite a better efficiency window than you would otherwise, thanks to a valuable donation of a local supplier. So, and so the home itself was highly energy efficient and really well done, I thought. So just a couple things to improve the continuous nature of the insulation. We had some issues with the thickness of the walls and the headers, and so we did not, in my opinion, get as well insulated in those headers and sills as we could have. So the next house looked a little bit better at the details of how we do that up front. Again, because we had a double stud wall, we have no thermal breaks. A typical stud wall will have thermal breaks, right? That stud bridges the insulation every 16 or 24 inches on center. But doing a double stud wall, 2x4s offset and staggered in the wall, we have a gap between those two 2x4 walls. So we don't have thermal breaks in the envelope. However, code requires fire stops in the exterior wall at 8 feet, and so those are our breaks. So it was something we did not know at the time. We had to add all that later. I did a lot of that work myself, which is fun.
This presentation has been brought to you by the Farm Energy Community of Practice at extension.org and the University of Nebraska Lincoln Extension. For more information, go to the websites provided, extension.org, bioenergy.unl.edu, or at YouTube, search CropWatch Bioenergy. For more information on zero net energy housing, the University of Wisconsin-Madison Extension has a website detailing policies and projects related to zero net energy. The website is provided at the bottom. I found it by searching Wisconsin Extension Zero Net Energy.